Hello, I'm Michael Burton. I'm from the School of Agricultural Environment at University of Western Australia, and this is a brief workshop on best-worst scaling. So this is part of a large project, ACL project, run by Lynn Crace at the University of South Australia, with a range of partners, as you can see on the screen. And as part of that project, we undertook some best-worst scaling studies, and it was thought useful if we were to actually provide some background materials for partners and beyond as to how this approach works. And so this is the purpose of this little workshop. Just to give some insight and overview as to how the techniques we've used in that project, what the basis, the theoretical basis, and how to apply them. So there's 5 sort of main areas, though I'm actually probably going to record them into four blocks to keep things short. We're going to just talk a little bit about conceptual issues and how you design one of these studies. Then what the model of choice is, as in what the model of behavior is underlying them, and then how you analyze that data, how you interpret and present the results, as in how you communicate to people as to what the outcome of the results. Part 4 is looking at a set of additional issues, not the simplest things, not the things that we've been doing in the basic things we've been doing in the project, but there are some other interesting developments going on about anchors, absolute rankings, consistency of choices. So I'm just going to touch briefly on that in part 4. And then finally, just resources and software. If you actually wanted to implement one of these, how can you go about it? The thing I want to make clear at the start is that this isn't a comprehensive course. It's going to be about an hour's worth of recordings here. This isn't a comprehensive course in best-worst scaling. But hopefully what it's going to do is give you an oversight and insight into what it can do. So if you can see that potentially it could be used in some study and for some application, then you've got a starting point to start thinking about how to implement and to apply. Okay, so let's start off with the conceptual issues as to what we're doing. So what is best-worst scaling trying to do? It's a method of generating rankings, and it's particularly going to be useful and applied where you want to quantify the difference between items. So it isn't just a matter of knowing what's best, but possibly to want to quantify the degree of difference between items. It's also particularly useful when you have a large number of items that you're trying to deal with. So up into the 10s, 20s, 30s, or whatever. Why is this coming to the fore as it is at the moment? Well, there's evidence that it's more efficient and more reliable than other methods. So you might just think of doing a Likert scale method of just saying, here's an item, say on a score from 1 to 7 as to how important it is to you, and then keep on doing that for all the items. So that's quite a common methodology that's been used, these Likert methods. And there's been various studies that have shown that best-worst scaling is more efficient in the sense that it can generate high-quality results relatively easily in terms of responses by people, and also more reliable in the sense that in terms of test-retest studies where people are asked to do the same study twice, the period of time between them, as in their responses are more reliable, and it also has greater external validity, as in when you're checking their responses against other measures, it seems as if these are giving a better score. So that's why we're starting to get to use these and to see this as being beneficial. Okay, importantly, there are 3 different types of best-worst scaling studies. They're called cases, case 1, 2, and 3. And then there's the object, the profile, and the multi-profile case. And you need to be clear as to what it is each of these does. we're actually going to focus mostly on case 1, but I'm just going to start off by giving you a quick run through all 3 so you can recognize what they are and where they might be used. So this is the case 1 object. We want to rate, as I said, a number of discrete objects, and these need to be definable as clearly sort of separate elements. So this is a study about, the example we've got here is a study about water providers from the perspective of a customer. What is the elements of the service that are provided by a water provider? What are these that you want to find out what is the best or the worst or the most preferred or least preferred element? And you can see here that there were about, I think, 14 items in this design, but what you have to do is you have to create subsets of these. So what the respondents see is a set of, well, these are the four of the set of items, and then all the respondent has to do is identify what is their least preferred and their most preferred, and they can just go into the survey and click one, click the other, and then they move on and look at another set. And we'll talk more about how the design is, but what you can see is this is just about objects, as in these are these unique components, and we have to pick the best and the worst elements of them. The case 2 is what is known as the profile approach, and that's where you might have a product or a policy and which contains multiple attributes, and what we're interested in is which elements of that product or that policy or whatever it might be, the object the item that we're interested in evaluating, what are the elements of it which are the most important. So you construct a version of the product. You see here, this is about buying beer, and it's asking, when you're going in to buy this product, okay, what are the most and least important characteristics of it when you're making that choice off the shelf? And you can see there are elements here: taste, country of origin, alcohol, whether it's organic or not, and you have to choose which is the most and which is the least important. And this is widely used. You can see this is going to be widely used in market research, where getting an idea about what the characteristics are of a product, say, that you want to understand. But you can see that in this way the items in some sense are subcomponents of something which you can think of as a single product. So that's the case 2 profile. And then the case 3 multi-profile, well, that's similar, except now we have bundles of these. So here, this is a water policy example, how people might think and prefer to see a water policy developed in terms of allocating water. And here you can see there are profiles. So the previous example, case 2, we had 1 profile. Here we now have 3 profiles labeled as option A, the current situation. There are these various attributes. Now these uniquely define it, and these will stay constant across all the profiles now, because then we can compare across these and say which of these profiles do we prefer. So similar, I have to pick the best and I have to pick the worst, as in this case the most preferred. I like this option most, I option this least, but essentially this is the best worst version, but I'm having to pick across a set of profiles. And this gives us a different sets of information. It gives us trade-offs within these elements and costs and so on. And this, for those who are familiar, this is basically a discrete choice experiment, but instead of asking just for the best option, we're also asking them for the least. So we're getting this best worst component to it. So those are the 3 types. But we want to focus on this case 1, this object based. This is going to be the focus for us today rather than the others. So, as I said, why not use Likert scales? Those are pretty commonly used, commonly available. Take each object, rate it on a scale, compare it across all the objects. Now, the challenge for that, for the respondent, is that you need to maintain this consistency in the way you calibrate the scale across the objects. So when I think of what a 5 is on my scale, from most good to bad, I have to keep that thought of what a 5 means the same across when I'm ranking all of the objects. And people can find that difficult to maintain that consistency in my scoring system. And then people in my sample may have different interpretations of what best and worst means, like the endpoints. So I give it if somebody's giving this a 7, are they thinking that is best in the same way as somebody else giving a 7? As in, am I giving a 7 because it's likely to be the best I think I could find in the market, or is it the best that I could possibly ever imagine ever existing? So what do these endpoints really mean? So that we can have problems on the interpersonal comparisons. There's also some evidence that people tend to cluster responses at the endpoints. So they want to say that, everything's always, say, the most important, very important. They don't want to discriminate between them. So there's various problems and issues with these Likert scales. And the best worst scaling is just found to avoid, to some degree, those issues. And this was a study which I was a part of. Didn't really do it. I helped with the experiment, but there are other people working with the conceptual issues and the design, working with young children, 5 and 6 year olds. So those would be a group who you might think would particularly struggle with the idea about how you scale things and score things. But what we found was that using this best worst scaling, more consistent, more reliable. So that sort of was a good indication that this approach is going to be useful. So question now is, how do we do the design? As I said, the case 1 best worst scaling is often used with large numbers of objects. 12, 20, 30 different objects might be in the set of things you're trying to rank. And so the fundamental component of a best worst scaling design for this case 1 is that it's repeated choices of best and worst. We don't just ask this question once of people, we ask them a whole series of questions. And we do that by generating subsets of items. So if we might have 20 items we want to rank, we don't ask them to choose the best and worst of 20. We show a subset, say, of 4 items, and ask them to pick the best and the worst from that 4. And then we show them another set, and then another set, and keep on repeating it. So you could think, well, we could go to the limit of that of just doing compared comparisons, as in just show them 2 items out of the set and pick every possible comparison or every possible combination of the 2 objects, and then we get a complete ranking quite quickly and a quick scaling of the entire set. So pair every object with every other, pick the best in each pair, repeat. So the problem is that starts to get really large quite quickly. So if you've got j objects, then the number of pairs is j times j minus 1 over 2. So you've got 10 objects you're trying to rank. If you do every possible pairwise, that's 45 pairs of data that people have to answer. And that's going to challenge them. Also, this isn't a particularly efficient way of doing that, of using their time. Because what you could imagine is that, well, if I just had 3 objects in each set, then I'm also going to get a complete ranking if they pick the best and the worst, because I know uniquely where the middle one is. So you can see that the paired comparison isn't necessarily efficient, and there must be more efficient ways of constructing a design. And there are, and the way that people do this is something usually using what's known as a balanced incomplete block design, BWSpart1v2. And they're going to be designs where we are going to have more than 2 items per block, or those questions, as in it won't just be pairs, it could be 3s or 4s or 5. It's balanced in that each item appears the same number of times across my complete number of designs, so I could offering them, let's say, 10 of these questions, and across the 10 questions each of my items will appear the same time, so that's what it means it's balanced. It also occurs with the other items the same number of times. So object 1 and object 2 will appear the same number of times as object 1 and object 3 appear together. But importantly, it's not a complete factorial. You could imagine you could construct a complete factorial where all possible combinations of items are appearing, and that will give you complete co-occurrence across at all levels, but we're not using complete factorials because complete factorials have the problem that it explodes again. We have much too many questions to ask people. A problem is BWSParts don't exist for all j, but the good thing is the catalogues of BWSParts do exist. So this is an example. This is coming out of the text by Louvre et al., which is in the reference at the end of this, which is a really good introduction to this. This is a table they produced, and they're showing examples of BWSParts. So what you can see is that if you've got 5 objects you're trying to rank, there's a BWSParts design where you ask them 5 questions. There are 4 items in each question. Each item is going to occur 4 times, and it will co-occur with the other elements 3 times. And then there's another version, if you've got 5 objects you want to do, where there are 10 sets, and then there are 3 items in each set. An item will appear 6 times across the entire set, so again it co-occurs 3. So what you can see is that there are different designs for different object numbers, and what they vary is in terms of the number of sets that we're going to have to create, the number of objects that are in, this is the set size, and then the co-occurrence and the occurrence. So what we're seeing here is, okay, here's where we're starting to hit a problem, as in the designs for 13, 14, 15, 16, none for 17 objects being reported, or 18, and then 19, and so on, because just the mathematics of putting together these balanced designs where we get every object appears an equal number of times and the co-occurrences are equal, imposes limits. But if you've got, if the number of objects you're trying to evaluate falls within one of these lists, then you have choices where you can just go and pick up a catalogue and basically look at a predefined design that becomes available to you. They can, if you don't have, if you have picked a number of objects that doesn't have a design, there are mechanisms you can do. They can also be generated in R if you're not off the catalogue. What do they look like? Well, this is an example of one. So this is a BWSPart for 9 objects. Again, this is coming out of the Louvre text. So we've got 9 items. This has picked up the version of the BWSPart where there are 12 questions, sets that are going to be asked, and the design just gives you the object numbers. So the first subset has got 2, 4, and 8. The next one's 1, 4, and 5. And if you went through this, you would find the occurrences. So we're going to have 1 is going to appear 1, 2, 3, 4 times, and we'll find that 2 will occur 4 times. 1, 2, 3, 4, and so on. And if you went through and looked at all the combinations, in terms of the number of co-occurrences, say between 1 and 4, it's going to be the same number of times as between the other items, 1 and 8, and so on. So they're going to appear equally, but what you'll notice is that they don't, all possible combinations don't exist. So object 1 is not appearing with all of the other 9 objects. That would end up with a full factorial. Is that an issue? Well, no, because you can ladder these together so you can get the full ranking, even though 1 may not appear with object 9, for example, which it doesn't. Does it? Just check that. No, but I can still get the ranking as to what the ranking is of 1 to 9 because I've got all these other comparisons going on. So it just ladders together. That's what the BWSPart design is doing. Then what do? Well, you don't want to have objects 2, 4, and 8. You actually have genuine objects, and this is one about locations. And you can see that object 2 is defined as K-12 education quality, 4 is parks and recreation, 8 is about broadband access and speed, and then wherever we can see in 8, we're going to see here broadband access and speed. So you just do a mapping across from numerically what's come out of the design. You just simply assign a real object to each of the numbers, and there you've got your best worst design. You can present these 3 items to somebody, ask them to pick their best and worst, and then these 3 items, and so on, and then we'll have the full design. So that's going to be the process. Okay, what if no BIBID exists for your J? There's some approaches that, again, as shown in Louvier, where you can mix and match out of existing designs, and you end up with something. Actually, you're starting to head towards something which looks more like a full factorial, but you might be able to get a design which doesn't actually lead to a full factorial. Or there are ways of getting approximations. So there's a software package called Sawtooth which will generate approximations of BIBID. They're not perfect, but they're not exactly balanced, for example. But they get close. So there's ways of implementing if you don't actually have something in the catalog. Okay, which is the best design to use? What you can see is that even if you do have a BIBID design in the catalog, you've got choices to make in terms of number of questions, and so on. So how do you make that choice? Well, in part it depends upon what your outcome is. If you want to estimate individual ranks, so if you want to use this data and to be able to report for an individual what the ranking is across your items, then the recommendation, and this is sort of a rule of thumb, is you need objects to occur at least 4 times. So you need at least 4 occurrences. So that sort of puts some constraint upon which versions of the design you might pick. And then there are other constraints, which is, well, some of those designs are ending up with large numbers of questions being presented to people, large numbers of these subsets. So how many choice sets do you think your respondent can cope with? Can they comfortably do 10 but not do 20? Well, is 20 just beyond the reach of what you think your respondents will be able to do? And that's going to be a judgment call depending upon the sample you're looking at. If these are experts who are well engaged, who are very familiar with the objects what you're talking about, then you may be able to get them to do large numbers. If they're not, if you're just recruiting general public or whatever, then you might have difficulty getting them to complete large sets, and so you may actually want to constrain that. And actually it's possible to do this actually where you show them subsets of the design, blocking as it's known, as we're doing discrete choice experiments. And in that case you won't be able to retrieve individual results so well, but you can do sample average results without a problem. This is a particular example where actually we went back to a paired comparison. Why did we go back to this? Well, this is because this is part of the project, the ACR project. Because of COVID restrictions, we ended up having to do this by phone. And it was just thought impossible to, or not impossible, really difficult to actually give people a list of 3 items and ask them to pick their best and worst, so that they couldn't have done 4, whatever. So just in terms of the implementation, we decided, well, we're going to have to go back to the paired choice, because we thought we could actually get people over the phone. We could describe 2 things to them and ask them to pick which was the most important. So that if you've got 2, you just need to make that one choice. So this was about design of water irrigation pumps, and so we could just describe 2 characteristics of the pump and ask them which is the most important if they had to choose between a pump setting. So as you can see, this question about design, there isn't some sort of absolute setting. It's all very much context driven in terms of what it is you're trying to achieve, and the people and the sample that you're trying to, the population you're trying to survey. Okay, so that's a good point to stop, and part 2 we'll move on to models of choice.